Starting off the nuclear chemistry unit, we're going to start with just a little review of isotopes. So for those of you that don't really remember anything about isotopes from first semester, here's your quick review. Isotopes, atoms of the same element having different mass numbers. So here I have 3 isotopes of hydrogen. After the hyphen here, so this is what we call hyphen notation, that's your mass number. Mass number is equal to protons plus neutrons. So in this case, 1 plus 0 gets me 1. Here, 1 plus 1 gets me 2. 1 plus 2 gets me 3. So this is hyphen notation. That's mass number here at the end. Protons plus neutrons. Pictures down here at the bottom. This is something we're going to talk a lot about in nuclear chemistry, is different isotopes of different elements are radioactive. So like this one, hydrogen 3, is radioactive, where these other ones are not, due to stability. Almost all elements have different isotopes, some, even up to 10. So again, kind of if you want to think of different flavors of the same atom. So can you guess which isotope is most common in nature? So we're looking at carbon 12, carbon 13, and carbon 14. Well, I know this one's not because it's unstable. So here I have a little toss-up, but if I go and look at my periodic table, the average atomic mass for carbon is 12.01. Well, 12.01 would be closer to this guy. So this one is the most common, and that's from my periodic table, that number down at the bottom, that average atomic mass. Again, a little more review. We talked about this hyphen notation, so that's our mass number here. The other thing you're going to see is nuclear notation or isotope notation. Mass number up top, atomic number on bottom, and then symbol here. Sometimes you'll have a charge, but not often will you have a charge. And really, for nuclear chemistry, we don't care too much about charge. It's a lot about mass number and atomic number. Atomic number is the same as our number of protons. Some isotopes are radioactive. So radioactivity is, by definition, an atom with an unstable nucleus. And because it's unstable, it emits energy and particles to try to become stable. So it starts getting rid of things until it's happy, till it's stable. Couple reasons for this: too many protons or neutrons in a nucleus. So this ratio of protons to neutrons is really important. Once you get to element 84, it doesn't matter. You are automatically going to be radioactive. You just have too much stuff stuck in that nucleus to be stable. And then there's some small ones too, like hydrogen 3 mentioned before. In terms of stability, so this is what we call the band of stability. Isotopes located along the edges are radioactive, where the black dots here are all of the stable isotopes that we know. And then there's a little second rule to this, the odd-even rule. So out of all 264 little black dots there, only 5 of them have odd numbers of protons and neutrons, where 157 of them have even numbers of protons and neutrons. So that's a good way, it makes for a good guess. If you see even protons, even neutrons, there's a good chance it's stable. So what determines whether it'll be radioactive? First thing, that neutron to proton ratio we mentioned before. So smaller stable atoms, usually 1 neutron for every proton, or the bigger ones. So as you start getting above, well, really kind of 20, it starts to climb to this 1.5 to 1 ratio. The reason: neutrons aid to increase the nuclear strong force in larger atoms. This is the force that holds everything together. So what you have is you have these protons repelling each other. They're positives, they're all trying to get away from each other because they're all the same charge. Neutrons are kind of like the glue. They hold it together along with this nuclear strong force. And again, once you get to 84 or more protons, it's just too big of a nucleus. So again, kind of looking at that again, neutrons are the gray ones, act as the glue to hold it together. The strong force is a force between each of these particles, kind of holding them together. The problem, so we get a small here, the strong force dominates, meaning it can hold this really easily together. It's a very stable element. But as you get to higher numbers of neutrons and protons, that force doesn't quite have the strength to hold them together because it's having to spread out a little bit. That's why these bigger elements become radioactive. Sorry, computer freaked out. So back to this, how to use band of stability. Really, what you need to know is that our ratio here, you get this 1 to 1.5 ratio. But looking at the graph here, numbers of neutrons, numbers of protons. Notice as the bigger and bigger you get more neutrons than protons. And really, this should stop right at about 84. And it goes a little further than that. But it should stop at about 84 because anything beyond this is unstable. Key things here, if you were off the band, doesn't exist. If you were at the edge of the band, you're unstable. And then if you are on the band, you are stable. So you are not radioactive if you are on the band here. Radioactive decay, so unstable nuclei, unstable, that's plural of nucleus, will emit particles. This is also called radiation, to become more stable. So like uranium emits these radioactive particles to become lead, which is stable. This is spontaneous, meaning you don't have to prompt it, it just does it, and it does this naturally. You don't have to do anything to the atom to make it do this. This is what we call transmutation. It gets its start from kind of chemistry. Where chemistry got its start was through this process, through this idea of alchemy. People wanted to get rich by turning elements into gold, and through Dalton we know that's impossible. But eventually we start learning more and more. Our instruments become better and better in science, and we do find that transmutation is possible, which is really the same thing. We are changing an atom of one element into a different element. That is your definition of transmutation. Most nuclear reactions involve changes in the number of protons. This is what changes our elements. So different numbers of protons gives us different numbers of elements. During these changes, this is where those particles are either absorbed or emitted. So it may do both, but then also you're getting a release of that energy. So between the energy and the particles, you fall to something stable. You get to a small enough element that you're stable. So different types of radiation you're going to see. Alpha, you're going to see it written like helium. Mass number 4 over atomic number 2, He. Beta, it's really a high energy electron, so it doesn't have a mass, but it does have a -1 charge, so it will end up increasing our atomic number. Positron is the opposite of a beta, so it's 0 over +1 electron. And then gamma, this is just energy, and I couldn't quite find, there it is over here. That should be a Greek letter, kind of a Greek letter gamma. It looks kind of like a Y. But here, no effect on no effect on atomic number, no effect on mass. This is just plain old energy, getting rid of that. So reasons this does solve a couple different problems. Alpha decay solves the problem of too many protons. Beta decay solves the problem of too many neutrons. Gamma decay solves the problem of too much energy in the nucleus. So going back to beta decay here, though, kind of a weird situation that a neutron actually splits into an electron and a proton. We don't have to show this, but this is what's happening in the within the atom, which is kind of a cool thing that you have one particle breaking up into a couple others. Alright, damage by type. Alpha is the weakest, so it's a big heavy element, or big heavy particle, not moving very fast, can't travel very far. Piece of paper will stop that for you. Still dangerous when inhaled or ingested. Same thing with beta. Beta moving a little quicker because it's smaller, but some clothing, some wood, a piece of aluminum foil, you can stop a beta particle. Again, only dangerous when inhaled or ingested. So if you're walking through a nuclear power plant that just just broke, can be dangerous, but those really aren't the ones we worry about. It's the gamma that we really worry about. Here, high energy, small particle will penetrate through multiple layers of concrete. I mean, you're talking feet of concrete that this gamma particle will move through. And when it does, it's going to start altering your DNA in your cells, causing that mutation. That mutation is usually what causes things like cancer and stuff like that. The other part of this, though, is we can actually use gamma particles to our advantage by firing them at or pointing them at a cancer cell. We alter that cancer cell's DNA, and now it can't replicate correctly, and you've now stopped the growth of a tumor. So both good and bad through gamma. Nuclear reactions, these very simple. All you have to know is that all you have to do is be able to add. So you see here the tops equal to 26. So if we go back, 226 is equal to 4 plus, well, what number would be up top? 222. On bottom, 88. If you think of the arrow as an equals, 2 plus what number? Well, that would be 86. So 222 over 86, and then use this number here on bottom to figure out your element. 86 is, just to double check, yes, this is radon right here for 86. So again, tops equal bottoms. That's law of conservation of matter. There is probably some gamma particles emitted here to get rid of that energy, but we don't show them. So again, just worry about making sure tops equal bottoms. Use your bottom number here, your new bottom number, to figure out what this element is from your periodic table. Another one, so you have technetium 99, atomic number 46. That's wrong. Atomic number 43. That should say 43 right here. Let's try that again. Well, again, my computer's freaking out here. Should say 43. So the reason why I wanted to show you this is a beta emission. So here's our beta particle. 0 over negative 1e. What I wanted you to see is that if this is 43, so negative 1 plus 44 gets me 43. People tend to confuse that a little bit. This is a minus, just remember. And again, 44 tells me that this is element Ru, which is like ruthenium. Again, gamma not shown.